This is Math 251, section 14.3. The title of this section in your book is Conservative and Source-Free Vector Fields, but there's actually something even bigger in this particular section. You all know that one of the big moments in Calc 1 is when you learn the fundamental theorem of calculus. Our study of conservative and source-free vector fields is actually going to lead us to a fundamental theorem of calculus for line integrals. As we'll see, we'll end up needing two of them, and that's going to be a theme that's going to continue throughout the rest of this chapter. We're going to have related theorems, but we'll have to have a form for the circulation integral and a form for the flux integral. That's just a little bit of a preview. Before I actually can get to that point, though, I do need to make this definition. I'll start with the idea of conservative vector fields. And here it is. A vector field F is called conservative if there exists what we call a potential function, phi, such that f is the gradient of phi. Why we call it conservative is something that I'm going to address sort of as we get a little bit further into here, but the idea of conservative or conservation is going to fit with some concepts that I think you've learned before in physics classes. Let's go ahead and go through some of the mechanics first, and then we'll get there. So, how do I know whether f is conservative? There's a little test, very simple in 2 dimensions. The test is that if our vector field f is defined as f comma g, then our function or our vector field is conservative if the derivative of f with respect to y is equal to the derivative of g with respect to x. So there's our sort of shorthand version of it. The test for a 3-dimensional vector field is a little bit more involved. You actually have to check that all 3 of these conditions hold true. Again, I'm just going to write them out in their shorthand form. F sub y must equal g sub x. Notice that's the same test as you had over here in the 2-dimensional case. But also, f sub z has to equal h sub x. And g sub z has to equal h sub y. So all 3 conditions must hold true in order for a 3-dimensional vector field to be conservative. All right, in order to get where we want to go, the FTC, it's going to be not only necessary to determine whether f is conservative, but to actually find the potential function. Find the phi whose gradient is equal to f. Okay? So what we're going to do is we'll check to see if things are conservative using these tests. And then we'll be able to find phi through some integration strategies that you'll see as we go through these next couple of examples. All right, so let's give this a try. In part A, here's our vector field f. Notice it's the rotational field. So we call this little f and little g. In our 2-dimensional test, f sub y equals g sub x. Well, f sub y, that would be -1. G sub x is +1, and so that's not true, so this is not conservative. Since it's not conservative, I don't need to try to find a potential function. One probably doesn't even exist. All right, let's try the second example. Here is my f. Here's my g. And again, the test is f sub y must equal g sub x. Derivative of f with respect to y, that would be 0, and that would give me a 4xy. Derivative of g with respect to x, that's going to be 0. That'll give me a 4x times y. And that'll be 0. So this one time it worked. Conservative. All right, now that I know it's conservative, I'd like to find that potential function, that phi. And remember, the gradient of phi must be equal to f. The gradient of phi is partial of phi with respect to x, partial of phi with respect to y. has to be equal to this. All right, I'm going to break this up, and I'm going to do each component separately. So I'm going to start with my first component, and I'm going to say the partial of phi with respect to x is equal to 4x cubed plus 2xy squared. If I just multiply by the dx, the differential, to bring it over here, again, don't let the partial versus the regular d throw you. It's just notation. And I'm going to now say, well, to find phi, I could just integrate both sides. So phi, integrating with respect to x, is going to be x to the fourth plus, again with respect to x, that would be x squared times the constant y squared. And when we do an integral, we typically have a plus c, but since this is an x integral, this constant c actually could depend on y. So I'm going to call that c of y to remind myself of that. All right, let's do the same thing with the second component. Partial of phi with respect to y has to equal 2y plus 2x squared y plus 3. And again, I'm going to go ahead and say if I were to multiply by the dy to bring it over here, then I could simply integrate both sides to get an expression for phi. Integrating dy will give me y squared plus x squared times the integral of 2y is y squared plus 3y plus a constant, but in this case the constant could depend on x. X's are getting treated as constants in this particular integral. All right, I now have two different looking expressions for phi, but I'm going to be able to bring them together if I've done everything right and make one function phi. First of all, I'm going to notice that x squared y squared is definitely part of phi. It's in both versions. So immediately I'll bring that down as part of my final answer. Then I just want to check to make sure that everything else works out okay. This c of y would correspond to the y squared plus 3y over here. Notice there are no x's in there. It's a function of y only. So that is the same as this. That means the y squared plus 3y is part of my answer. It replaces the c of y. Similarly, this x to the fourth could correspond to that c of x. It's a function of x only, and so I can put x to the fourth in my final answer. It corresponds to c of x. So all of these pieces are represented in both forms, one way or the other. And there's my potential function. There's my phi. This should happen every time. The constants should work out if you truly had a conservative function to start with and if you've done all of your integration correctly. If it doesn't, you might want to go back and check on that. All right, let's try a couple of three-dimensional examples. Okay, so in the three-dimensional situation, we have got, I'm just going to recopy this condition over on my page so that we have it to work with. F sub y has to equal g sub x. F sub z must equal h sub x. And g sub z has to equal h sub y. There's the f, the g, and the h. And f with respect to y is 2. G with respect to x is also 2. So far, so good. f sub z, that's going to be -1, must equal h sub x, but that's 2. And already I know it's not going to work. I don't have to even bother checking the last one. This is not conservative. Not conservative, no need to try to find a potential function. All right, what about this one? Well, here's the f, the g, and the h. And I've got my headings right up here, so I'm just going to go ahead and test them again. F sub y would be z. G with respect to x would also be z. So far, so good. F with respect to z is going to be y. H with respect to x is also going to be y. Looking good. One last test. G with respect to z is going to be x. And h with respect to y is also going to be x. This is conservative. Since it's conservative, I can find a potential function. And the condition on my potential function is the gradient of phi must equal f. Since this is three-dimensional, my gradient's going to have 3 terms. Like so. And then I'm just going to go through and I'm going to do exactly the same thing as we did last time. I'm going to say if I equate the first components, partial phi partial x equals yz minus x. I'm going to bring the dx over, and I'm going to integrate. Integral with respect to x, that's a constant, so I'll get x times that constant yz minus 1/2 x squared plus c. But since this is an x integral, my constant could depend on, both y and z. Second component, partial of phi with respect to y equals xz. Bring the dy over and integrate. And this is constant with respect to y, so we're just going to get xz times y, or xyz, plus a constant, but that could depend on both x and z since y is the only variable here. And then finally the third component, partial of phi with respect to z, equals xy plus 2. Bring the dz over and integrate. Constant with respect to z, so I'm just going to get xy times z, plus another constant, so 2z, plus a constant that could depend on x and y, since the only variable here is z. All right, I want to put all this together and come up with one function that represents phi. And I'll start by saying that xyz is definitely part of all 3 answers. So xyz is absolutely going to be part of my final answer. This 1/2 negative 1/2 x squared, it could be in the c of x and z, since there's only x's, so x's and z's are fine. And it could also be in the c of x and y. So there's some place that fits in every single integral to represent that. So I'm good with that. And then finally this 2z, same idea here. C of x and z could contain the 2z. It's got z's in it, is okay. And here, c of y and z, that's all right with that 2z. So the plus 2z is going to work. Again, every term that you have represented here should work. I'm just kind of going back over and double checking to make sure. So there's my potential function, phi. All right, why don't we pause there, and before we start getting into the fundamental theorem of calculus, we've got our test for conservative. We'll use that in the FTC in the next video.